Hi, give me 1 second. Okay, this looks good. Okay, hi, so this is going to be a talk about how we don't just see an object moving, but when we see them move, we attribute the motion to forces like internal or external forces. Again, my name is Nguyen. Thank you for coming to my talk. So when we see an object move, we also make rich inferences about the physical forces that act on those objects in order to explain their motion. For example, when we view a movie clip such as this, we don't just see that the bugs are moving, but we also see why they are moving, which is due to the forces that are being exerted on them by the water. And this is critically important in order, for example, to predict what will happen next if the bugs let go of the branch. Right? So there's plenty of evidence that people can reason about physical forces. For example, McCloskey et al. 1980 found that people commonly incorrectly predict that an object exiting a curved tube will follow a nonlinear trajectory upon exiting. Battaglia et al. 2013 also suggested that people can make judgments about whether the tower will fall. But do we also perceive physical forces? So recent work suggests that physical forces may be presented in a more immediate and perceptual way. For example, physical information is integrated into specific visual processes like attentive tracking and visual detection. So a key to test of whether forces are really recovered perceptually is whether they interact with the perception of other visual features. So does the perception of forces influence how we see objects move? So in experiment 1, participants were asked to complete an acceleration detection experiment in which each trial features a moving dot. There were 32 upward trials and 32 downward trials, and they must indicate after each trial whether the dot accelerated or remained at a constant speed. In both the upward and downward conditions, the dot will accelerate on half of the trial and remain at a constant speed on the other half. First, let's take a look at an upward moving object accelerating. Here it is again. And here is the same exact acceleration now performed by a downwardly moving object, which looks more like a slider moving down a hill. Here it is again. As you can see, compared to the acceleration of the upwardly moving object, this acceleration is far less noticeable. So for both the upward and downward conditions, we computed D-pram. D-pram is a measure of sensitivity which factor out response biases. And we found that participants better at acceleration detection for objects that move upward. And we want to make sure that this is not just a random result. We ran a study again on the new 100 subjects. And we found the same result. So these results are quite amazing, and it suggests that the perception of acceleration really is better when objects move opposite to gravity. These results align with past research on how self-propulsion make things look alive. For example, in Tremolet-Fuhrman 2006 paper, where observer viewed a moving dot, when the dots changed heading, the same heading changes were judged to be less alive looking. In the condition where there were present of the paddles, the paddle makes those heading changes look like bouncing. But when the paddle were absent, those heading changes are more alive looking, and those heading changes appear to be self-propelled. Brad et al. 2010 also suggested that self-propelled looking heading changes also capture attention in a broke detection task. So given the past results, it is intriguing that in our experiments, the speed increase was more noticeable when objects were moving upward, such that those speed changes could only be explained by internal forces within the object, which causes to overcome the pervasive force of gravity. But there is another possible interpretation of this pattern of results, which is it could either be an advantage for speed changes that resist gravity or disadvantage of speed changes that consistent with gravity. So we want to test whether subjects are more sensitive to speed changes that go opposite to the force of gravity. And to find out if there really is an advantage for that and not just the disadvantage for going consistently with gravity, all we have to do is to compare upward acceleration to a different baseline. So in this case, using this new horizontal baseline, if the subjects are better at detecting speed-ups when it goes upward compared to horizontally, then that has to be due to an advantage for objects that go opposite with gravity. Here is an example of that displays. So the upward condition was just like the upward condition in the previous study. The object sped up on half of the trial and remained at a constant speed on the other half. But now, instead of the downward condition, we use the horizontally moving control conditions. And here is an example of that displays. So half of these observers, the horizontal trial feature a rightward motion, and for the other half, the horizontal trials feature the leftward motion, and none of the results depend on this. So relative to gravity neutral horizontal baseline, you might ask, how do subjects do in detecting upward speed change now? And we found that there really is an advantage for objects that move upward. And we also ran a study again, a new sample of 100 subjects. And we found the same results. So the perception of acceleration really is better when objects move opposite to gravity. So just out of curiosity, with 100 different observers, we have them detect downward or gravity consistent speed changes relative to horizontal baseline. Here is an example of the displays. Here is an example of the horizontal baseline display that you've seen before. And here are the results from 100 participants in the acceleration detection. We found that participants worse at acceleration detection for objects that move downward. And just to make sure, we run it again on a new sample of 100 subjects each. And we found the same results. So these results suggest that the perception of acceleration is worse when objects appear to be consistent with gravity. And it turned out there are a bit of what we may call gravity blindness effect. So from the previous results, we can see that subjects are both better at detecting acceleration when it's go opposite to gravity and worse at detecting acceleration when it's go downward or consistent with typical gravitational acceleration. So resisting gravity does indeed confer a benefit and performance. And that theory makes an exact opposite prediction for deceleration. Now, if an object slows down and moving upward, that's perfectly congruent with gravity. But if an object is moving downward and slow down, that's opposite to typical gravitational deceleration, because if you think about it, it can only happen if there's some force resisting gravity. So in experiment 3, observer view half upward and half downward trials. In both conditions, the dot decelerated on half of the trial and remained at a constant speed on the other. And observer reported after each trial whether or not the dot decelerated. Now, let's take a look at an upward moving object decelerating. Here, the same exact deceleration now performed by a downwardly moving object. Here we again computed DBRAM. Compared to the previous experiment, here the pattern of results perfectly reversed, with more sensitivity to deceleration when it was performed by downward moving object compared to upward moving ones. And we also ran a study again on a new sample of 100 subjects. We also found the same result, which is that subjects were better at detecting deceleration when it were opposite to the force of gravity compared to one that were consistent with the force of gravity. So to repeat, we had a better detection of deceleration when the object went downward, and third, resisted typical gravitational deceleration compared to upward, which is when they were consistent with typical gravitational deceleration. So this pattern of results had two different interpretations. It could be due to an advantage for deceleration opposite to gravity, or disadvantage for deceleration consistent with gravity. So in our final experiment, we asked subjects to detect deceleration relative to horizontal baseline. For half of the trials, the dot will move downward and the dot will move horizontally on the other half. Here is an example of that display. So here again, the downward condition was just like the downward condition in the previous study. The object slowed down on half of the trial and remained at a constant speed on the other half. But now we use horizontally moving control condition instead of upward condition. Here is an example of horizontal baseline display. And for half of these observers, the horizontal trial featured a rightward motion, and for the other half is leftward motion. However, again, none of the results depend on this. And here are the results from 100 participants in a deceleration detection. So relative to gravity neutral horizontal baseline, we found that there is an advantage for objects that move downward. And just to make sure, we run it again, a new sample of 100 subjects. And we found the same results. These results suggest that the perception of deceleration is better when objects appear to opposite gravity. But you might also be curious, how about moving with gravity relative to horizontal baseline? So we also ran a version with the upward moving object compared to horizontal baseline. And here is an example of that display, which is the same display that was used in a previous experiment. Just a reminder, here is an example of a horizontal baseline display that you've seen before. And here are the results from 100 participants in the deceleration detection. We found that participants worse at deceleration detection for objects that move upward. We also ran a study again on a new sample of 100 subjects. And we found the same results. So these results again suggest that the perception of deceleration is worse when objects appear to be consistent with gravity. The experiment collectively shown that there was a better detection of speed changes opposite to gravity, and we also found participants were worse in detecting speed changes that consistent with gravity. And in general, the results strongly suggest that our perception of objects' movement depend on the forces that inferred to be acting on or in them. At the start of this presentation, I suggest that one way to test whether we perceive physical forces rather than just reasoning about them is to test for a way in which seeing forces influences the perception of other features. So all four of these experiments support the conclusion that the perception of physical forces is a richly interactive part of visual processing, and that the hidden forces that are automatically inferred to be acting object can have a surprisingly big influence on our perception of how objects move. Thank you for listening and enjoy Koksai.
Thank you, Hong. We have 7 minutes for questions. David, on virtual space, why don't you go ahead?
Yes, thank you. Thank you for your presentation. I almost wonder if there might be an effect of frame rate, because some of those animations, it looks as if the ball was actually not moving continuously up or down. It actually looked like there were some instances where it would actually like skip and jump around. And so I wonder if that would interfere with subjects' ability to make accurate judgments about acceleration.
Thank you for the questions. It's actually my fault. I should have optimized for video clip. I think that the video through Zoom is a little glitchy. But if you're interested, I can send you a link to the experiment itself, and I'm like sure that is not like jumping like you see on the Zoom. Sorry about that.
No, it's okay. Thank you. I appreciate that clarification.
Yeah.
All right, looks like we have an in-person question.
There is a question in chat.
Yeah, we'll go with the in-person and then we'll come back to the chat.
Is that me, Lilia?
That is you.
Hi, Lilia.
Hi.
Hong, that was a great talk and a really elegant set of experiments. I have a question that is really simplistic, that sort of goes back to the logic behind all the experiments. I feel like I understand the results, but I don't feel like I understand the logic by which the results support the conclusion that we're perceiving forces as opposed to inferring them or reasoning about them.
So I mean, yes, there's past research saying that when when predicting and intercepting the moving object, observer clearly perform better when those objects change speed in a way that roughly consistent with gravity. But what I'm trying to say that when it comes to what we noticed in the first place, gravity-based expectation may have the opposite effect. I hope that answers your questions.
So your expectations change what you see.
Yes.
So is that evidence that the forces are being perceived the way edges are detected in vision? Like I'm just not. I'm interested in the question, and I don't understand what result would have supported the conclusion that we are sensitive to gravity, but we're not perceiving forces. Right. The question is, maybe I misunderstand the claim. I thought the claim was that we are perceiving forces as opposed to just reasoning about them or just inferring them. What result would have contradicted the claim that we're perceiving the forces and supported the conclusion that we're just inferring them or reasoning about them?
So for our task participant, this is a 2 AFC task. So the participant have to detect whether there is a speed change or not, and the results show that like when the object accelerated upward, the participant is more like sensitive to detect that speed change compared to the downwardly moving objects. Is that how?
Sure, I think I do understand the result. So is the claim, maybe I'm misinterpreting, is the claim about distinguishing perception from inference, or is it just that people are sensitive to people's perception of the stimuli is sensitive to these assumptions about gravity?
Sensitive to assumption of gravity.
Okay, thank you.
Thank you for the question.
Okay, I will go ahead and read this question in the chat. This is from Safa Andak, says, thanks for the talk. Did participants follow the stimulus? If that's the case, do you think that these results are also affected by the eye movements?
Thank you for the question, Safa. That's a really good question. It's possible. However, we don't look at the eyes movement yet. So we don't have the answer for that, but thank you for the questions. We should take a look at it. Thank you.
Okay, and we have time for one more question. Looks like an in-person question.
Hi, yeah, great talk. I wanted to ask about the horizontal movements. If I followed correctly, the horizontal, I know it was just treated as a control. I think all of them went from left to right. I'm wondering.
And also right to left.
Oh, you did. Did
Yeah.
you find differences in the right to left versus left to right? You could imagine reasons to expect those.
No, unfortunately, or luckily, we didn't find any effect between right to left or left to right. I think I did mention that in the talk. Maybe I went too fast.
Oh, sorry, I must
Yeah,
have missed
sorry
it.
about that. No.
Thanks very much for clarifying.
Okay, no problem.